All right, I hope you're not getting sick of talking about heart rate. I don't know why the last two examples have both been heart rates, but here it is again. One indicator of physical fitness is resting pulse rate, so how fast your heart's beating when you're not exercising. 10 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. Their resting pulse rate, again we're measuring beats per minute, were measured before the test began and then again after 6 weeks. Is there evidence that this kind of exercise can reduce resting pulse rates? The idea is the more you exercise, then you're actually healthier, and when you're not exercising, your heart doesn't have to work as hard. So that's the idea here. I want to point out why this is very different than what we did in the last chapter. So here's some of my here's my data. Here's my 10 guys. Yes, their names are humorous for a reason. Look at it. Note, I have 2 groups of data. I have before data and I have after data. In no way, shape, or form are these sets of data independent. These 2 groups are not independent. What? Why are they not independent? Because they're from the same person. Alan's pulse rate before he exercised and Alan's pulse rate after are affected by the fact that they are both Alan. David's pulse rate before definitely affects David's pulse rate after. It was higher than Alan's. So David, whatever it is about him, his diet, his genetics, his weight, causes these 2 things to be very much related. So these groups are not independent. That means what we learned in chapter 24, like gone, whammy, can't use it. Instead, we need to come up with a new technique. This is what we call paired data. You'll notice pairs because each person has its own pair of data. So we're going to calculate it a little bit differently. In order to really look at this data, we're going to look at the differences. If I'm really going to compare before and after, it's only fair if I look person by person. For example, Alan, for some reason, this exercise didn't affect him at all. He had a difference of 0. What do I mean? I mean when I subtract these 2 numbers. Brandon's heart rate was 83 before. It went down to 79, so he had a difference of 4. Carlos had a difference of 4. I'm trying to spot somebody who's actually went up, so we can see how that's a little different. Let's look at Ivan. Ivan had a difference of -1. Because his pulse rate actually went up after the exercise routine. So we're going to do our whole hypothesis test on the differences. We're going to ignore the other 2 columns of data. We're going to create our own new data called the differences. And we're going to conduct our hypothesis test there. So to get started, we should probably put the data into our calculator. So you will notice that I put mine in list 4 and list 5. Now you'll notice my list 6 is filled in, but I'm going to show you how to do that. Please do not type in list 6. Just 4 and 5. I'm going to show you a shortcut because I love shortcuts. You guys are going to like this. So what I was doing here was I was taking the value in list 1, subtracting the value in list 2 to get my difference. Value in list 1 minus value in list 2, get my difference. My calculator can do that all at the same time. I'm going to take my list 4, subtract my list 5, and I'm going to store it in list 6. It's pretty cool, right? So you should go and verify like it's in list 6. You don't have to type it in. Pretty cool. All right. So now the question is, Ms. Curtis, how do we actually conduct the hypothesis test? Well, same 4 steps. As a matter of fact, I'm going to encourage you to think as we're going about chapter 23. What we do here is very similar to chapter 23. It is not similar to chapter 24. Watch for that. All right, so step 1, I'm going to specify an alpha level, 0.05. I'm going to write my hypotheses. My hypothesis is going to be about the average difference. What? Okay, so I wrote mu, and this is a subscript D, D for difference. Very common notation to use. What do you mean the average difference? I mean, I'm going to look at all these differences, and I'm thinking about the average value. So this data no longer exists. I don't even care about it. I'm just focusing on the differences, and I'm looking for the true value of the average. Ms. Curtis, can't we find the average? We could add all these things up and divide by 10. That would be X bar, sample. I'm thinking all the men in the planet that use this, exercise. If the exercise doesn't do anything, I would think that the average difference would be 0. Okay, pause and think about that for a minute. Oh yeah, if their pulse is the same before and after, I'd get a difference of 0. All right, if the machine is effective, let's think about what value that would be compared to 0. Well, let's see. If we start out that they have a big heart rate, and then it goes small. So this is the before minus the after. That would be effective. My heart rate was higher. It gets smaller after doing this. That's good. It means I'm becoming more healthy. So I'm going to get positive values. That means I want the average difference to be bigger than 0. Positive values. Okay, please stop, pause the video. Think about that until you feel good about it. Next step, of course, I'm going to check my conditions. The first thing it asks for is random. I don't recall, so of course I would read it through here. It says 10 men volunteered. So they are not random individuals, they are volunteers. That is very common in experiments. Okay. So I'm going to point out that we do have volunteers. Not random, may or may not even be representative, but that's very common in experiments. Nearly normal. I need a histogram. But Ms. Curtis, there are 2 sets of data. Don't you need 2 histograms? No. Remember, those 2 sets of data, they don't exist anymore. I only care about the differences. And so when I create my histogram, I'm creating a histogram of differences. Oh, this is weird. Okay, so in my calculator, remember, list 6 is where we stored the differences. So when I create my histogram, I'm creating a histogram of list 6. Check it out there, list 6. I'll do a zoom 9, and I apologize, I've got an extra line in there. But we can see more or less, I don't know, that's kind of funky looking. Notice my axis is right here. So this box over here, remember we had that one guy had a difference of -1. That's why we have an extra line in there. All right, so I'm going to try to draw that the best I can. It looks kind of like this with one here. And it got even taller. Oops. And then there was like a space and one over here. I'm actually kind of concerned about that. I did only have a sample size of 10. That is pretty small. So central limit theorem can't save me here. I'm worried. This is unimodal, but not symmetric. Ms. Curtis, what does it mean if our conditions aren't satisfied? It means our results are questionable. But it's cool. We finished the problem. All right, the last chapter we kept talking about independent groups. This is no longer necessary. As a matter of fact, we don't have independent groups. We have paired data. That's why we're doing chapter 25. So if you're trying to verify independent groups, the answer is going to be no. You don't need to write it down. You can just identify we're doing paired groups. For that reason, this is called a paired t-test. All right, so I've written hypotheses. I've checked my conditions. I'm a little bit worried about them, but I'll keep going. And I can move on now to my mathematics. I'm going to have a t-squared, I'm going to have a p-value, and I'm going to have degrees of freedom. My t-score, you can kind of picture in your mind. Here's my little t model. Looks like the normal model. It's going to be centered at 0. This value always comes from the null hypothesis. And I'm going to think about whatever difference I actually observe. That's frequently called d bar instead of x bar, the average difference. I would subtract 0, because that's the center. And I'm going to divide by my standard deviation over the square root of n. This is my typical SE we've been using. All right, I'm going to have my calculator help me out with some of these values. So, as you might expect, I'm going to go to stat, and I'm going to go to test. You will not find a paired t-test in here anywhere. We just use the t-test, and we know in our brains that it's paired. So I'm going to select t-test. I actually have data this time around. Notice the null is set at 0, but I could replace that if it was something else. There's my list 6. I need to select the proper alternative hypothesis, and that's this greater than. And then I can calculate. Let's see what we got. There's my t-score, my p-value, my x-bar, but remembering we're secretly calling this d-bar now. And there's my s and my n, so all the pieces I need. All right, so I'm going to show in red things that must be. You must write the t-score formula with the values plugged in. So remember, d-bar, that's the same as x-bar. We're just calling it d-bar just to remind you what the difference is. So I'm going to fill in 2.2, that's from the calculator, minus 0 over s is 3.12 approximately over the square root of 10. And I just copy straight from the calculator. I know that that t-score is 2.23, like cool, done. My p-value, I don't have to get it from my calculator using the whole, well, it wouldn't be normal CDF, it would be TCDF. No, I'm just going to copy down. It's 0.026. Degrees of freedom, well, let's see. It doesn't list it there. That's because, remember, it's n minus 1. We saw that back in chapter 23. Same thing here. So I would record my degrees of freedom. It's 10 minus 1. That's 9. It's important, required. You have to include the degrees of freedom. All right, so last thing is for me to write a conclusion. Well, let's remember my p-value, 0.026, is definitely smaller than my alpha level. Just note to yourself, recall alpha equals 0.05, so we're smaller. That means we reject the null hypothesis. Please don't write null, write null hypothesis. That means there is evidence. Evidence of what? I always go back to the story problem. Let's see what they asked us to show. Is there evidence that this kind of exercise can reduce resting pulse rates? Yes. We've shown that the pulse rates went down. So I'm going to say that there is evidence that this kind of exercise can reduce resting pulse rates. All right, I hope you will stop there unless you are still concerned about reduce. I'm going to talk about that one more time, but you can be done if you're done. Several of you, I can hear it. You're saying, Ms. Curtis, if it said reduce, then why the heck did you do a greater than sign? Shouldn't it be a less than sign? And again, my reasoning is here. It has to do with the order that I subtracted. To reduce resting pulse rates means this afterwards would be the smaller value. Big number minus small number is positive differences. That's why I selected the greater than. All right, I hope that's clear. If not, please keep asking me about it.